So, indeed, coalgebra is, at least in the sense that I mean it, is, which we could call universal coalgebra, is a kind of general systems theory, particularly in the context of theoretical computer science over the last 15 or 20 years, developed quite vigorously over the last 10 or 15 years, which leads to a number of novel notions. We all know about induction, but probably unless we specifically come across coalgebra, it hasn't occurred to us that there would be something such as co-induction. The reason for talking about this here in the context of the QICS school is that certainly I've been doing some recent work. I think other people, Jacobs, who's here, are also interested in a new kind of application of coalgebra, not to classical computation, but because it is this rather rich and expressive systems theory, to apply to modeling and reasoning about physical systems, especially quantum systems, with a view to applications, of course, in quantum information and also in foundations of quantum mechanics. So it turns out, and we'll sort of see this a bit rather briefly at the end, that this raises some new challenges for coalgebra, I think of an interesting kind, and they can be met in an interesting way. So we'll sort of see that at the end. We'll also see novel connections with another kind of systems model that's been studied quite extensively, so-called Q spaces, which have been developed in the context of linear logic and computer science again, but actually relate in a very natural way to the kind of structures that have been studied for many years in the foundations of quantum mechanics. Perhaps starting off with Mackey's famous book on mathematical foundations of quantum mechanics, which has been a kind of source point for many subsequent developments. And we'll see that these natural models of quantum systems get a new twist when we look at them from a categorical perspective, essentially because we look at morphisms quite carefully as well as the objects themselves, and that they connect up with coalgebra again in a somewhat new and surprising way. So, since this is an audience of diverse interests and background, my plan is to start off by giving a general introduction to coalgebra in this sense, not assuming very much at all by way of certainly the knowledge of category theory. I assume you do know what a category is, and by now this is clear, but I will remind you what a function is. I hope you will also know what that is.
I don't think anybody has defined that yet.
I hope everyone knows anyway, but I shall define it. So there we are. I'm filling a gap, need it or not. So, and then, but of course, anyway, all right. So, I mean, on the other hand, functors have been used already in the tensor products and so on. Anyway, having given a bit of a general introduction, we'll then look at some of the applications to quantum mechanics. So a gentle general introduction, then I'm afraid what will be a somewhat faster look at the applications as time allows. Okay, so let's begin with coalgebra, a bit of general orientation. Now there are specific forms of coalgebra that have been widely studied in mathematics and mathematical physics in recent years, things like Hopf algebras, Frobenius algebras and so on, which are usually studied in the context of various kinds of linear algebras. That's not the particular kind of coalgebra that we'll be looking at here, although of course there's a sort of broad relationship. So that's the reason for distinguishing this by calling it universal coalgebra, which is a phrase that's used here. So this is more of a general systems theory, and the term is suggested by universal algebra, which again, something that not necessarily everyone is familiar with, but gives a general way of looking at algebraic systems. In a similar way, universal coalgebra gives a general way of looking at behavioral systems, giving them a mathematical structure and uncovering general notions that are applicable to many situations. And part of the charm of this coalgebra is that while it does need some category theory language, it doesn't need very much to get up and running. Actually, you can do a great deal just working over the category of sets and functions, which implicitly we're all familiar with. That's a good thing, and we can tread relatively lightly in terms of the underlying category theory. On the other hand, it does really need category theory, because whereas algebra, of course, is something that's familiar, and we could all kind of say in some sense what an algebra was without using any category theory, it's actually pretty hard to say what a coalgebra is without using the language of category theory. In particular, we need at least to know what a functor is. And functoriality is really a kind of central idea in looking at coalgebra. So, in fact, I'm therefore going to give a brief recap of what a functor is. Now, the reason in fact, an old sort of dictum of the founders of category theory was that categories were only introduced to allow functors to be defined, and actually then functors were only introduced to allow natural transformations to be defined. But in some sense, the general philosophy in category theory is don't just look at the objects, take the morphisms into account too. Of course, category theory should take its own medicine, and the interesting thing is, I mean, indeed it does, and interesting things happen. So we apply this to categories as well, and therefore we need to know what a morphism of categories is. And the answer to that question is a functor. What is a functor between category C and D? So firstly, it assigns an object of D to every object of C, and then it assigns an arrow of D to every object of C in a fashion respecting source and target. The obvious sensible fashion is, if we think of the sort of a graph of a category, or the way that we could write a diagram of arrows, of objects and arrows in a category, then at least the functor has to preserve the shape of any such diagram. If you had an arrow from A to B in the diagram in C, this picture gets translated to a corresponding picture in D. And of course, since categories are more than graphs, there's also a condition that goes with this, that the categorical operations of composition and identities have to be preserved. And this is a big deal. A lot of modern mathematical textbooks almost go out of their way to avoid mentioning category theory explicitly, but really these notions are everywhere, and in particular the notion of functoriality, this idea of an assignment of this kind, mapping one kind of mathematical structure to another in a way that preserves composition and identities. It's one of the key notions of, say modern mathematics, the mathematics of the second half of the 20th century, which is still very much with us. Okay, so let's immediately pass to a few examples. So I'm just going to look at functors on the category of sets. So hopefully everything is concrete and simple, and even if the notation is slightly unfamiliar, the ideas are straightforward. And here I'll just focus on functors of one variable to keep things simple. That will mostly do for our purposes. And the first example is the so-called categorical sum or coproduct. So thinking of it in set and just applying it to a single argument, we're taking a sum of two copies of x. So we should think of this in a more concrete way as a disjoint union. So we make two copies of x and put them together to make a new set. A reason, the justification for calling this a sum, if you think of x as, say, as a finite set to keep things simple, then the cardinality of this disjoint union is the sum of the cardinalities of the components. So disjointness exactly guarantees that. There's no overlap. And then we have products, which would be familiar. Cartesian product, again, just taking it with one argument. So really this is a power, x squared. And again, terminology is also justified by appeal to cardinalities. We can fix a coefficient, so we can fix a set A and build that into the definition of the functor and just multiply by the fixed set A. And exponentiate. So we have the power set construction. This is the covariant power set, which just maps, extends a mapping on the underlying sets to the power set in the pointwise fashion. And again, by cardinalities, we can think of what we know by Cantor's theorem or whatever, it's going back to Cantor, that the cardinality of P of x is 2 to the x. So, and we can also take fixed exponents. This is something that will come in later in an important way, but this is a simple construction as it stands because we fixed the exponent here. Now what this means is x to the a is the set of all functions from the fixed set a into x. And this gives a perfectly good covariant functor. Actually, it might just be worth something about that. Is the board visible?
Samson.
Use that one.
Samson, can you use that one, please, for the
This
camera?
one?
Yeah.
Okay. But this is still... So, x to the a. So if I have a map from x to y, I can push it forward to a map from x to the a to y to the a. So I start off with an element of here, which by definition is a map from the fixed set a into x, and I translate it into a map to from the fixed set a into y by composition with a given function g. So this is fine, and we get a functor, and everything is easy to check. But notice that if we took this not as fixed, but as a variable, we'd get a problem. In other words, if you take x to the y and allow y to vary, then there is a natural way of making this functorial, but it goes contravariantly rather than covariantly. Let's keep the x fixed and keep the base fixed and vary the exponent. Then you can see that there's a formula similar to this one, which given, say, h going from y prime to y.
That's invisible down there.
Nothing is visible down there, you're telling me that. So, is this visible?
If you go up.
I'll go up, okay. So the point is, we want to, induce a mapping from, of this kind, and we can do that if we're given a map, say h, that goes from y prime to y. This is the direction it has to go in. And then we can take some, what did I have? Say, I have a k that goes from y to x, in other words, something that lives in here. So k is in here. And by precomposing it with this h, I get a map that goes from y prime to x. So this works, and it's functorial, but it's functorial in this contravariant sense, that the direction of the arrows get reversed. So this is not the kind of thing that we're encompassing here, and it's not the kind of thing that coalgebra usually deals with. But it is the kind of thing we're eventually going to want to deal with from the point of view of modelling physical systems, as we'll see. So we'll keep that in mind. But for the time being, we shall carry on with these simple kinds of functors. If we compose out of this quite small set, then we get what are often known as, for obvious reasons, as the polynomial functors, where you just have sums and products and constant coefficients. Or if we allow the power set as well, we would get exponential polynomial functors. So a small and simple set, but it turns out already very expressive for many modelling purposes. Okay, so those are functors. Now what are coalgebras? Unfortunately, this is easy to say. And we can give it in complete generality, but in practice we'll mostly just deal with simple functors over sets of the kind that we just been describing in our examples. But in generality, if you're given an endofunctor, meaning simply a functor from a category to itself, same domain and codomain, then a coalgebra for that functor is just an arrow of this shape. This goes from A to F of A. So you think of A as the carrier of the coalgebra, and we'll actually see that the good way of looking at this is to think of it as a kind of state space, while we think of F of A as showing how we evolve with some observable behavior into a new state. That is generally the way that we'll be able to read the examples that we'll look at. Of course, the definition principle is much more general, as the notions will develop, will apply in this great generality. And of course, taking the categorical philosophy as always, we must say not just what coalgebras are, but what the morphisms of coalgebras are. So, well, we don't be ugly to speak of co-homomorphism, so usually one just says F coalgebra homomorphism, or just say morphism is just an arrow on the carriers that makes this obvious square here. That gives us, in an obvious way, a new category. So we started off with a functor and we built a new category of coalgebras from it. And again, this passage from functors to categories will be important at a later, well, a much later stage of what we're doing here. Here it's just the basic notion to get us started with this idea. Okay, so to get a feel for how these ideas work, let's just take a first very simple example. So consider this very simple example of a, so we could allow in our polynomial functors constant functors as well. And then this thing is a very simple example of a polynomial functor. Here's the sum. And then here's something with the identity to x, and then this is a constant functor which is valued at this thing I'm writing as 1. And here 1 is supposed to be any one element set, if we're working in the category of sets. And this has a special status because it's any such set, any such one element set is a terminal object in the set. And by definition then, once we've said what this functor is, a coalgebra is simply a map that looks like that. So there's some given set A that we specify and some function that we specify of that shape. So, of course it's very simple, but there's a kind of scenario that goes with it, which will give us a general prototype for how we can interpret a much wider class of such things. So this is a sort of operational scenario. We can think of this as describing a very simple kind of system. So we think of A as the state space, which in principle is unknown. And what can we do to interact with it? We were saying we can experiment and actually in the early literature of automata, there was a lot of work about experiments and trying to discover the state of an unknown system. So what could we do? Well, the idea is we have a run button, and there are two possible outcomes of pressing the run button. Either, so there's some kind of continuously flickering light, let's imagine, let's say it's, I don't know, orange or something. Either the system keeps running, so although we don't know what state it's in, we know that it's still running, or the system comes to a stop, in which case some red light comes on, and then we know that it's stopped. And this is what we're reading into this map here. If we go from some input state, which we started off in here, into this one element set, then that's where the red light comes on and we've stopped, and nothing else can be done with the system. On the other hand, if the system keeps running, the light keeps flickering, then we know that we could press the button again and something else might happen. So it's a very limited kind of interaction indeed. And basically what we can see is that the only observable information we could extract by performing a sequence of such experiments on the system is that we press the button some number of times and eventually the system terminates. And of course we might keep pressing it forever and the system might just be going in a loop and might never terminate. So it's not a very interesting kind of system, but nevertheless there is that much information in it. So there are actually infinitely many different types of experience we can have even by interacting with possible systems of this kind. Well, so we could specify any coalgebra we liked of that form, any set, any function. And it turns out that all the information we could extract from any coalgebra can all be expressed in one single coalgebra. And in some sense, the meaning of any system or of any state in any system is completely specified by an image and interpretation that it has in this one canonical coalgebra. And in this case, so this one special coalgebra encapsulates exactly this observable behavior. And in this special case, we can describe it very simply. But again, bear in mind that the point of this is that this is giving, in a very simple example, an idea that extends in great generality, as we'll see shortly. But here, more or less building on the discussion we gave previously, we can define it very concretely. It's the natural numbers extended with some, the carrier is the natural numbers extended with some additional element that rises infinity for the obvious reason. And my coalgebra map in this one specific coalgebra that I'm defining looks like this. We think of it as a kind of predecessor map. So you might think that this sort of has a, well, I'm using the natural numbers here, so there's something going on. We might have time to say a bit more about that later. But predecessor of 0 takes us into this special element here, into the stop. So it stops when you're at 0. So in some sense, 0 is telling us you have no button presses allowed to you, and as soon as you do press the button, you go into the stop state where the red line comes on. And on the other hand, for n plus 1, in the obvious fashion, we decrement and go back into a state here that you can now press the button n times, whereas this thing is actually goes back to itself, this special element of infinity that we've added. So that is a coalgebra for this functor. Why do I say that it's special? Well, given any coalgebra whatsoever for this functor, we can define a coalgebra homomorphism from that coalgebra into this special one. And we can see that what this is doing is essentially extracting the information we described in our operational scenario, which is exactly there. All the information we need to describe the outcome of any such scenario is there, and so we get a unique record of what could happen with any such system. So if we take any state at all, we can simply use the coalgebra map to chase down the behavior. We see there are two cases. Each one is a sort of unique orbit that we get tracking through the state space of this coalgebra. Either after n button presses, we end up in this special element here, so we stop. In which case we assign n by our map, or we're going to be in an infinite trajectory where we keep on being able to press the button and then we assign infinity. And it's easy to see, to check, that this is a coalgebra homomorphism. It's exactly doing what it's forced to do in order to preserve the behavior, and formally to define that condition that perhaps you could recall. Yeah, this one here. So chasing around that square exactly corresponds to preserving the behavior, and that's what we're doing when we. But not only is it something we can define, it's the only one that we can define. It really is forced. Nothing else, no other assignment that we could make would preserve the behavior in this way. So there's exactly one coalgebra homomorphism from any given coalgebra to our special one. That's the sense in which it's special. And in fact, the sort of formal category theoretic statement of this is that this particular coalgebra that we've defined is a terminal coalgebra, which is to say just that it's a terminal object in the category of coalgebras and their homomorphisms, where terminal, let me say this somewhere, yes, here, is just has its usual meaning that for every object in the category there's a unique homomorphism to that special terminal object. So this thing, it has the same universal property in the category of coalgebras for this functor that a one-element set does in the category of sets and arbitrary functions. Okay, and this is our little property that we have. Now, the point is that this is something that makes sense for any functor and for any category of coalgebras. So it's a, so to speak, a first general systems notion that we've extracted by looking at these kind of considerations. But it has an immediate sort of import in modelling terms, because it's saying that terminal coalgebras are encapsulating exactly the observable behaviour of systems. In fact, if you have a terminal coalgebra for a given functor, we can think of it as inducing a fully abstract semantics for arbitrary systems of this type. Because given any such coalgebra, we can map it uniquely to the terminal one in a behaviour-preserving manner. So there's a canonical map, which one and only one that preserves the behaviour, and each element, each state of the arbitrary coalgebra gets mapped to its meaning in a unique fashion. Okay, so maybe we can extract some general features of this notion of terminal coalgebra. So the first one is not only trivial, but trivially trivial. As it's been said that the purpose of category theory is to distinguish those things that are trivially trivial. Because any terminal object in any category is unique up to unique isomorphism. That should be the first category theoretic proof that one sees. On the other hand, the second one is not difficult, but it's actually a beautiful fact with a beautiful elementary proof, and I thought I'd give it. This is the Lambeck lemma, which says that this is not immediate from just general considerations about terminal objects. So it's saying if you have a coalgebra which is terminal, which has this property of terminality, then that arrow is an isomorphism. So it's saying that the object is completely specified up to isomorphism, and its behavior map is an isomorphism. So to be is to be an observable behavior. And
sorry, you said terminal again, but did you mean final? Or
final and terminal, I'm afraid, I treat as synonyms.
Okay.
So I try to use terminal consistently in this talk, but I may have switched to the other one at various points, but they're complete synonyms for this talk. Yes. Thanks for pointing that out. So here's the proof. I mean, it's a lovely proof. It's simple, but very nice. So here is our assumed terminal coalgebra alpha. And we can simply apply f, the functor f, to this coalgebra to get another coalgebra. It's not very demanding to be a coalgebra. We just need an arrow of the appropriate shape. And because functors preserve source and target, this thing is also a coalgebra. Now we know that this thing is terminal, so there's a unique coalgebra morphism from this one to that one, which we call H. And the coalgebra homomorphism property means that this diagram commutes. On the other hand, of course, we can take this arrow alpha we were given here and make this little diagram where we see that this trivially commutes, and hence this top square is a coalgebra homomorphism too. Okay. Now, if we paste together two coalgebra homomorphisms like this, then certainly they compose. I mean, this is the way you define the category of coalgebras, and therefore we see that this composite, alpha followed by H, is a coalgebra homomorphism from A to A. But now we remember that A is by definition, or A alpha is by definition terminal, so there's a unique coalgebra homomorphism from any coalgebra to it, in particular from itself to itself. There's only one coalgebra homomorphism from A to A. And the perfectly good one is, of course, the identity. So since the identity is 1, and since this composite is 1, they must be the same. So at this point, we've shown that this composite is the identity. And of course, H is our candidate for the inverse of alpha. To complete the argument, we have to show that the composition the other way around is also the identity, this time on f of A. But this then becomes a little computation from this diagram using exactly functoriality. In some sense, this is the sort of nicest elementary argument that exactly shows all the working parts of functoriality. So this composite in the other order, well, by the coalgebra homomorphism property, the diagram commutation here is equal to this composition. Functoriality preserving composition lets us pull the f out here. By what we proved in the first step, we know that this is the identity, and now functoriality in the sense of preserving identities lets us conclude here. And therefore, we have the inverse to alpha. So, final coalgebras are specified in a very tight sense. And what the states are really determined by this functorial fixed computation. Now, of course, we just looked at one very simple example, so the next thing we should point out is that simply by varying the functor f, we can apply all these notions and many more to a very wide range of operational and observational scenarios. And we get common notions and common theorems that apply to all of these directly. And in this sense, we get a rather general theory of systems whose state evolves on the time, which are subject to some kind of observable interactions. And we can actually get a very rich collection of such scenarios, encompassing, for example, much of traditional automata theory in computer science, with the simple examples of functors we've already mentioned. I'll just add one more, for probabilistic behavior. So we're keeping everything very simple. I'm just taking the, I think I have to apologize a bit because Prakash is in the audience and he uses much kind of fancier versions of this functor. Here we're just taking probability distributions on a set with finite support. So 0 and all the finitely many values, so everything keeps simple. And this is a covariant functor with, and the way you push morphisms forward is in the obvious fashion. And all sums work because everything's finite. Okay, so that's just one more functor, and now we can begin to describe a lot of these different scenarios. So let's fix a set of inputs I and outputs O, which kind of give us some standard way of sort of having an interface to an observer. So as a first kind of thing, we could consider deterministic transducers. So this is the type so what we're doing is we're using the functor to give us the type of behavior or of observations we can have with a system of a given type. So here is something built out of the simple ingredients, constant coefficients, fixed exponent that we saw earlier. So for each state, we map it to the set of functions from the set of inputs to a pair consisting of an output and a new element and another element of the set. So that's the functor. And then a coalgebra is a function of this shape, s going to f of s. And therefore it corresponds to a function which we read in the following way. S is a state space, I'll probably say this, no I don't. S is a state space, so it maps a set, a state S, and then an input I to a pair consisting of an output and a new state. And we could write this as a transition in this fashion. And this is deterministic in the sense that for each state and each input, there's exactly one such transition. So you see, this is exactly on the nose, a very standard notion of transducer. Now, if we standardize our output set, think of it as just accept and reject, and again, this will chime in with something we'll see in a physical context later, then this gives us a certain notion of acceptor, not quite the one you would meet in a textbook, but close enough for our purposes. And I'll write the input set as sigma, thinking of it as an alphabet in the usual fashion. We can uncarry alpha, so we can shift the input over to the left. And then it looks like something that will be familiar to you if you've ever looked at any text on automata theory. We have our set of states S, input alphabet sigma, and what the automaton does, or deterministic automaton does, is specify a mapping, which for each state we could be in an input symbol we could get, either accepts or rejects the word it is either accepting or rejecting and moves to a new state. So to see if a word is accepted starting from a given state that we might pick out as an initial state, just drive this through letter by letter on the word and see if you end up in, with an accept as the final output. And that would give you exactly the usual notion of an acceptor. Okay, so this is all deterministic, but it's a very simple matter in this framework to go to a non-deterministic case. You simply use the power set functor, which now, for a given input, gives us a set of these possible transitions. So for each state and input, there's a set of possible transitions producing an output and moving to a new state. So this is exactly encapsulated by this functor here using the power set. And we can, if we want to go probabilistic, we simply replace the power set by this functor of this discrete probabilities functor, which gives us a probability distribution on these possible transitions with an output and moving to a new state. So we can think of them as transitions as before, but now weighted by probabilities. And we can even be simpler and still get notions that have actually been extremely widely studied and applied in computer science. So for example, we could forget about outputs altogether, so the O disappears. You can think of it as, say, as a one-point set, so there's no information in it, and we still get something useful, this idea of labeled transition systems. Given an input, simply may evolve to some new state, with any one of a set of possible new states on receiving this input. And notice that this is equivalent to having a set of transitions like this, which is the way that this functor is often written. These two things are isomorphic. Set value functions are the same things as relations. So therefore, coalgebras for this functor specify simple transitions of this kind. These things are used very widely in the study of concurrent systems in computer science. They're also closely related to Kripke structures as used in modal logic. And we can go even simpler and still get something which is rather interesting, actually, from a mathematical foundational point of view. We can even forget about the inputs as well as the outputs. And we still get something interesting, which is a novel way of looking at set theory, which is, after all, a sort of basic topic. So now we're taking a behavioral view of a set. So what's the behavior of a set? Well, you can think of a set as being able to evolve into any of its elements. Or if you think of a set as a tree, then the membership tree, so all of these things are members of this set here, then the arrows now transitions are going to run in this natural direction down the tree.
Why do they have to be trees?
Well, they don't have to be trees, but the sets we're familiar with are described by membership trees. But indeed, they don't have to be trees, and let's indeed look at some pictures. So firstly, it's good, one thing that is nice about labeled transition systems is that we can draw very simple pictures of them. So this is a coalgebra. Here are the states, and this is the coalgebra for labeled transition systems function we were just describing a moment ago. Over here. So it's sets of things like this. So this is that algebra map exactly. And actually you see that there are lots of these finite structures giving us quite tangible and concrete behaviors. We begin to see why, on the one hand, we have some quite abstract structural mathematics, but on the other hand, it connects to very concrete things that we can actually even represent in the computer and compute with. And actually, even in this bare case of sets, I mean, you might be thinking, if I stripped away the inputs and the outputs, there doesn't seem to be any interaction with the environment at all. But in a sense, there still is, because implicitly, if you have a set of things, we've actually still got that idea we saw in our first simple example, because there might be nothing at all you could get as, that it could evolve into. This would be the empty set, which is just represented by one state here with no transitions. On the other hand, this set has this clearly different behavior, and so on. And indeed, since you just accepted looking at transition systems that might well have loops in them, if we simplify matters a bit and go to sets, there's really no reason why we shouldn't have loops there as well, as Prakash was just pointing out. So this is also a picture of a set, but not of one of the traditional kind that is accepted in the usual set theory, where we have the foundation axiom, which is there exactly to prohibit such things. And one of the points of this study is it provides general context where these things seem to make perfectly good sense. So this is a simple example of a non-well-founded set that has an infinite chain of membership relations, but in a rather simple fashion. Okay, so one issue that clearly arises here, I mean I already appealed to it at some point informally, is that we can look at these pictures, but we want to know when two different pictures really correspond to the same behavior. Whoops. So for example, in this system here, really we can see there's no difference between state 1 and state 2. Whether I start here or I start here, the upshot is I can keep doing an A as many times as I like. So I'll never tell the difference between this system and the one that only has one state with that loop. And certainly what we intend is that this unique homomorphism into the final coalgebra, if we have a final coalgebra, that identifies states that have the same observable behavior. But in order to validate that, we need to have an independent way of characterizing what this means. So let's begin by defining, and this is one of the fundamental points that comes up in coalgebra. So let's define a suitable notion in the concrete case of labeled transition systems. And this is actually already was a classic notion in computer science in the study of concurrency before coalgebra came into prominence. So this is a concrete thing that applies to labeled transition systems. It gives a general answer to this question of when two states should be considered to be equivalent, which takes account of this idea that because you have this non-determinism, you have various kinds of non-deterministic branching. So if I'm in a state, then I may evolve by an A to one state or to another state, and I don't really know which one it is. So what can I say about the behavior? And the idea of a bisimulation is that it's a relation on states which keeps matching their behaviors. So if state S is related to state T, and S has some transition to a new state S prime, then T has a matching transition. So it can also do an A and get to some state T prime. So it mustn't be stuck for an A. So we remember those cases where the node had no way of evolving. And moreover, when the state it evolves to, there must be some state it evolves to with an A, which continues to match the state that the first one is evolved to. So this is indeed a kind of inductive all the way down. It's actually a co-inductive relation. And there's a matching condition. So it's supposed to be a symmetric relationship. So anything either can do, the other can match it, and we keep within the relation. In fact, I've defined this here on a single transition system, but it could easily be extended to have relations between states in different transition systems. We can compare states in different systems in terms of their common scenario of observable behavior. And we write this twiddle for this relation if there is some relation which does relate. So in fact, bisimulation is the largest bisimulation. And another way of looking at it is that we take things to be equivalent unless we can observe a difference between them. So it's identity of indiscernibles. And there are some simple examples here. This first one is essentially the little example we looked at. Here's an X that does an A and then loops back. And this one does one A and immediately loops back. There's no difference between them identified. If we take two systems and identify them at their roots, then again there'll be no difference. There's sort of two copies of each state you might evolve to, but those copies will have the the same behavior, so we might just as well have that one copy. And this is an important and key example, it's called the so-called branching time notion of something of two behaviors that are not deemed to be equivalent under this definition. So if we think of a little transition system like this, and one that goes like this, you see the possible runs along the branches, the language, if you like, that we could read off from these two are the same. You can get A followed by B and A followed by C, and those are the maximal runs you can have. On the other hand, they're not bisimilar because if I can do a move under an A here, which takes me to a state which cannot be matched by any state here. It's not matched by this first state, because this first state, while it can do a B, can't do a C, and this one can do a C, and symmetrically for this one. So,
So when you talk about what's observable in these systems, all that's observable is whether you're allowed to make transitions.
Yes, in this particular functor, that's exactly what's observable. Yes. So again, we can use this metaphor of the buttons. Now I have a whole set of buttons corresponding to my different actions, and if I try and press them, either it refuses to press down because I can't do it, or it does press down. I know I've evolved to some other state. That's exactly the scenario that corresponds to this. This is not the only notion of equivalence that can be considered in that general context, but it is a fundamental one, and others can also be sort of reached through varying the coalgebraic setup. This is a fundamental thing, particularly in its general form, because it turns out that what we just defined concretely can be defined in full generality, at least for any endofunctor on sets, and actually well beyond that once you have enough structure around to talk about relations. So here is, so we say a relation, so a relation on the states, the carrier of a given coalgebra. So in a natural way we'll have projections onto the states, first and second projections. It's a sub-object of the product. So we say it's a bisimulation for the functor f. Exactly if there's some coalgebra structure on the relation which makes this diagram. And that turns out to be, if we translate the previous definition of bisimulation in these terms, it comes to exactly this. And of course the beauty of this is that it can be applied to any endofunctor and we get a notion of bisimulation. So we get a very general notion of behavioral equivalence, which is specified by the very functor itself. Okay, so we'll go through the technicalities, but let me give some sort of key properties here that makes this into a sort of useful, in fact, a rather powerful theory. Under various mild assumptions we might make on the functor, particularly preservation of weak pullbacks for the first one, bisimulation is an equivalence relation. For this one, bisimulation is an equivalence relation. And if a terminal coalgebra exists, then we get what we wanted. Equality in the final coalgebra semantics is exactly bisimulation equivalence. So bisimulation is defined for any transition system. It's an equivalence relation. What equivalence relation is it? It's exactly the kernel of the unique coalgebra homomorphism into a final coalgebra. So in that sense, we really have validated the idea that the final coalgebra semantics is a fully abstract one for this notion of behavioral equivalence. Moreover, and actually, I mean, by the way, if you take this definition, there's no reason at all why S and I could have used a different system here. So I have a perfectly good notion that relates different coalgebra states in different coalgebras. That works fine. And of course, they all have coalgebra homomorphisms in the final coalgebra. Yeah.
I just want to see this functor f.
Yes.
With r to f of r.
Oh, you want that again? Yeah.
Yeah. So, what's its interpretation again?
Well, so R is the relation, which is supposed to be the bisimulation. So remember, in terms of our concrete definition, whoops, are we? Yeah. So R is the relation on states, and if we think about what it's saying here, so of course these transitions are exactly what are given by the coalgebra map. So it's saying if I have a pair of states, then I can evolve them to pairs in a way that preserves the transition relations on both sides. That's the. So that's what this is saying.
I have another question about that slide. When you say delta is a coalgebra map of
Yes.
above, you just mean that
Here, it just means it's a map.
it's not a map of coalgebras, it's just any more.
No, sorry. Sorry, I should have just said if there is a coalgebra structure
Yeah.
on R, which makes this commute.
Correct.
Yes, that's all. Right enough. Yes, being a coalgebra in this sense, as I've already said, is very undemanding. But of course, making that diagram commute says something. It's preserving the structure on both sides. Exactly that sort of matching behaviour thing that we saw concretely.
If you wanted to do this in a category other than set, what do you need on R for this to work?
Well, you need to have enough of a calculus of relations. So, a regular category.
The underlying functor is on set, but you take it up to the F of R, is that how it works?
Yes, yes.
And you need to be able to do that.
Well, I mean, actually, this makes sense. I mean, if we're just working with sets, or any sort of regular category, this makes sense anyway, because R is, after all, a set. And F of R is a set, therefore. And this is a function, so it makes sense. You don't need much, and actually, you need even less than this suggests. So, taking advantage of this fact that we can even have bisimulation between different systems, we can also, it's easy to see that coalgebra homomorphisms are themselves examples of bisimulations. In other words, if I have a coalgebra homomorphism from one coalgebra to another, then if, so here's A alpha and B beta, and here's my coalgebra homomorphism, then any little a here is going to be bisimilar to H of A. So coalgebra homomorphisms automatically preserve behavior, which is what we'd expect, but particularly when you map into the final coalgebra, you're mapping to something that has the same behavior that you have, and that holds for any coalgebra homomorphism. In fact, that leads to another, in some respects, more robust notion of behavioral equivalence, which nowadays is sometimes preferred to bisimulation, and we can even get rid of most of these. But this is very useful, and I like it. So, and I think it's easy to motivate. Now, there are also mild assumptions we can make on F, not the same ones as here, under which, so this is general assumptions under which a terminal F coalgebra does exist. So we now know this is an interesting thing to have. It gives us this kind of final coalgebra semantics. And we can actually know in advance that most of the functors we'll encounter in practice do actually have them. By the way, these apply to all the examples we've seen, with a sole proviso, as you might expect, that if you're dealing with power set, it's a bit of a dangerous beastie, so you need some kind of size restriction. So we might only consider the finite subsets, or if we like infinite sets, we might consider only all the sets up to a certain size for some cardinality, or some cardinal that has reasonably nice behavior. So certainly in accessible cardinal would work very well. Or we could even, yeah, I think that's, or we could work with classes and take the construction that gives you all the set size sub-collections of the class, and that works fine too. So under very wide conditions, we get these terminal coalgebras and everything works very nicely. So you see the beginnings of a beautiful general picture emerging. Okay, so here I'd like to, at this general level, relate this a little bit to sort of ongoing discussion in foundations of physics. I'm not saying it sort of provides immediate answers, but it kind of could maybe usefully inform some of those discussions. And this is really this idea, a long-standing discussion or debate about whether to take an ontic or an epistemic stance towards the states of a quantum system in particular. In other words, is psi something that really exists out there objectively, or is it a way of summarizing our possible states of knowledge about some physical system? And in some sense, I think the coalgebra point of view sort of reconciles these two positions. On the one hand, we can definitely think of it as a state-based approach. And we've basically been reading, interpreting the elements of the carrier as states, but in a way that emphasizes that the meanings of the states lies in their observable behavior. And in fact, as we've seen in the terminal coalgebra, which gives you this universal semantics for these systems of a given type, the states are determined exactly as their possible observable behaviors. In some sense, we're solving, under this notion of observable behavior, to construct uniquely up to isomorphism what the state space should be. And states are identified exactly if they have the same observable behavior. So I'll just leave that thought. Okay, so in general, the subject has been developed quite extensively. Particularly important that there's been a big development of coalgebraic logic for reasoning about observable behaviors of systems. So there's a natural way of describing properties of states that meshes with the kind of ideas we've been discussing so far. In fact, labeled transition systems, as I mentioned, are very close to Kripke structures, which are the standard way of interpreting modal logics. We can understand this coalgebraic logic as a sort of generalization of modal logic, where for each functor you get a new flavor of modal logic that it can be used for those kind of systems. And the way this ties in with what we've already been discussing is this nice connection with bisimulation. Two states will satisfy the same formulas in the logic if and only if they're bisimilar. So, and from a point of view of sort of understanding and predicting the behaviors of a system, this sort of slots into the sort of verification paradigm of computer science. Moreover, and this is a very nice point, the logic can be read automatically off from the type functor. And there are now also strong results for reading off decision procedures which describe complexity for these logic and algorithmic tools to support these. So it's quite a nice picture. And for this general introduction, let me finish off with a couple of useful references. An early one that I think very useful is this paper by Jan Rutten on universal coalgebra. And sitting quietly in the back of the room here is Bart Jacobs, a leading figure in the work on coalgebra. And he has a very nice but unfortunately as yet incomplete book, which I hope he'll finish soon. He's made it available. Sorry?
I need a sabbatical to finish it.
Yes.
Just
Maybe you're distracted by comments tonight. I've just been spending the last 2 months here visiting us. So anyway, these are both very useful resources. Okay, how much time? Half an hour. I'm afraid things are going to speed up a bit now. But anyway, I hope this was a sort of useful general introduction. So now I want to come on to the topic of representing physical systems. And here's the general paradigm I would like to describe. It's actually not at all new. It's a very sort of, it's a paradigm that's already sort of played an important role in the foundations of physics and foundations of quantum mechanics in particular. But again, we look at it from a slightly new point of view. So we take a system to be specified by a set of states and a set of questions that are asked of the system. So we can think of observations, but we're focusing here in particular on yes-no kind of questions. And in general, the the result of asking a question in a given state will be probabilistic. So this could apply to a classical system, applies very nicely in the case of classical statistical mechanics, or it could apply to a quantum system. So the way that this is all specified is by a function of this form, which given a state and a question gives you the probability that the question will receive the answer yes when the system is in state S. And this is essentially the point of view taken by George Mackey in his classic book on mathematical foundations of quantum mechanics. The question, which I think goes back to him, maybe earlier, and might be Berghoff and von Neumann, is preferable to property, since in quantum mechanics in particular we can't think of static properties which are determinately possessed by a given state, and questions have this right connotation of the dynamic act of asking by performing a measurement. So for this reason we could call such structures Mackey triples, and if you don't like that name, well, you can blame it on Alex Wills. Okay, so in particular, how do we fit quantum systems into this format? So a quantum system with a Hilbert space H as its state space will look at like this. H0 is a set of non-zero vectors, so we're not normalizing, we're taking arbitrary vectors as representatives of states. L of H is the set of closed subspaces of H, which in the usual way, or you can think of the projectors equivalently, correspond to the yes-no questions of quantum mechanics. And the evaluation function is the statistical algorithm, as some people like to call it, giving the basic predictive content of quantum mechanics. So, in effect, this summarizes the basic ingredients of the Dirac-von Neumann style formulation of quantum mechanics into the definition of this Mackey triple. So, now, the obvious next step of the story would be to show how these Mackey triples could be viewed as coalgebras. Things aren't quite that simple. There's actually a subtle point or two that means that these triples can't immediately be viewed as coalgebras. We will eventually do that. The story has a happy ending, of course, but it involves some innovations in coalgebra. So in fact, our strategy is firstly to make a more transparent connection to another general systems model, in some ways simpler, in some ways also more general, or allowing more flexibility in some respects, and then to show how these are called Q spaces, and then to show how Q spaces can be subsumed in a suitable version of coalgebra. But we need to give a little stir something additional into the coalgebra pot by taking a simplified version. And basically, this story follows the contents of these two papers, which are both available on the archive. In particular, the one about the coalgebra side of the story is to appear in Lick's next in a few weeks. Right. So, what's a Q space? Well, I can now give a pretty quick answer. A Q space is a Mackey triple. We're slightly more general, but of course, again, this can be defined more generally. This construction was originally given in an appendix to Mike Barr's monograph on star autonomous categories. But as it happens, they also have a lineage from George Mackey, from his PhD thesis on dual pairings of topological vector spaces. So we're working just in sets here to keep everything simple. We parameterize on this set K, which is going to be some set of truth values or whatever. And the Q space over K is a structure like this. So we have a set of points, as they're usually called in the Q space context, and a set of attributes, and an evaluation function which for each point of attribute gives us a value in this fixed set K. So we see that Mackey triples are exactly Q spaces over the unit interval. Importantly, Q spaces also have morphisms. They have a full categorical development, and actually the construction gives you a very interesting way of constructing dual categories, star autonomous categories, and so on, which originally motivated this construction. So a morphism between two of these things is given by a pair of maps, one going forward on the points, or the states if we think of them as Mackey triples, and the other going back on the attributes, which we can think of as the questions from the Mackey triples point of view. And this should make us prick up our ears, because we saw that in this situation with exponentiation, we needed a backwards map to make exponentiation in a variable exponent functorial. And the condition is that this evaluation is preserved under this map, starting from a state in here in the domain and an attribute in the codomain, but this sort of formal adjoint-like relation is preserved. So that's what a tune morphism is. And the morphisms composed in the obvious fashion, we just compose the maps on the states or points in the forward, we push them forward by composition, and the backwards maps goes in the opposite direction, which makes a category which has a very rich structure, most of which we're not going to look at here. Now again, because this is a very general theory, we can formulate general systems notions in this context. So in particular, if we think of states and attributes, each kind of allows us to make discriminations in the other under the evaluation function. So we can say that a choose space is extensional if whenever you get the same outcomes by evaluating two given attributes on any possible state, that actually they must be equal. So this is no distinction between attributes without a difference on some state. And on the other hand, we can play the same game for the points. In this case, we say it's separated if whenever you get the same answers for all attributes, the points are actually the same. And it's bi-extensional if it has both these properties. In particular, we'll mainly be interested in the case of where things are extensional. And we'll be interested in the equivalence relation we get on states if they give the same answers under all attributes. And there's a canonical way of collapsing a given system into one that is separated by factoring it through this equivalence. So this is all completely general for choose spaces. And actually, it could be done in greater generality than abstract category in some structure. Okay, so this is all very simple. What we want to show is that this simple systems theory lets us pick out, when we look at the particular cases of Hilbert spaces as Mackey triples in this setting, some of the main salient notions. So we get a full and faithful representation of the groupoid of Hilbert spaces with their physical symmetries in the category of choose spaces, which of course uses Wigner's theorem but with a certain twist to it. I think some of the development is quite interesting. And the interesting point here is that unitarity or anti-unitarity is essentially forced on us by the mere requirement of being an assumed morphism. And we don't even need to assume that the mapping is projective. So firstly, at the basic level, we look at the Mackey triples or choose spaces arising from Hilbert spaces in the way that we've already described. We get some standard properties, but in particular, we can easily see that this general notion of equivalence that applies to any choose space holds in this case exactly when two vectors are on the same ray, when they're projectively equivalent. So the quotient by the equivalency is exactly the passage from unnormalized vectors to rays. The same, I mean, there's a sort of another chapter of this for mixed states, and the same thing holds there. Okay, so we've recovered that notion there. More substantially, we're going to see that tube morphisms, just by looking at tube morphisms, are semi-unitary. So recall that a semi-unitary map between Hilbert spaces is a bijective map which is additive and which presents scalar multiplication up to either exactly or up to complex conjugation, and also, obviously, in a product. So it's an isomorphism of the inner, taking into account the inner product structure. So it really preserves everything inside. Of course, these are the sort of fundamental symmetries of quantum systems. Here's the basic result we extract. We go through the details. So we consider Hilbert spaces of any dimension greater than 2, could be infinite dimension. We look at, and so we make them into Mackey triples or Chu spaces. And we now look at any Chu morphism, which is just a pair of set theoretic functions of this kind, satisfying this formal evaluation relation. But for any vector or any ray, I should say here, this is the projective collapse, which, as we saw, is the bi-extensional collapse of this Mackey triple. So these are the rays. So for any ray we take here, and for any closed subspace we take here, then the formal evaluation is preserved. And we need to assume that the forward map here is injective. But we don't need to assume that it's surjective. And under those assumptions, there's a semi-unitary which gives rise to this, semi-unitary on the underlying Hilbert space that gives rise to this, which is unique up to a phase. Okay, this terminology is just the projective lift in the usual fashion. So we have a mapping on vectors, then it maps rays to rays. And the big picture is that we can take a category with Hilbert spaces and semi-unitary maps, which compose in the evident fashion. So we can compose unitaries and anti-unitaries perfectly well, and they compose according to the rule of signs, as it were. This category is a groupoid, and these semi-unitaries are physically significant symmetries of Hilbert space. So the usual dynamics is given by a continuous one-parameter group, and by continuity they actually have to be unitaries. But some important physical symmetries are represented by anti-symmetries. So they're all meaningful in some sense. And the basic result is that here's our bi-extensional Chu spaces with injective forward maps. And we get a functor from this category of Hilbert spaces and symmetries into these Chu spaces. And this functor is full and faithful. So in fact, to get this, we have to factor into the projective version of this symmetry group, or in other words, we have to identify unitaries or semi-unitaries which differ only by a global phase. So it's just a natural generalization of the projective unitary group. Okay, so that tells us that starting off just with the observational content of Hilbert spaces as Mackey triples, we've actually determined by the Chu morphism condition exactly what the right notion of symmetry is. An interesting technical point is that surjectivity comes for free. Okay, now all of this was with Chu spaces or Mackey triples valued over the unit interval. So we can ask whether it's, so we're getting probabilities of getting the answer yes to a given question in a given state. And we can ask the question now whether it's necessary to use the unit interval as the value space in order to achieve this representation result. Can it still be achieved if we collapse the unit interval, even define that in many values? And actually, given any function, a set of values k to a set of values l, in an obvious fashion by composition, it induces a functor from Chu spaces from Chu spaces over k to Chu spaces over l. And if you had a morphism, it's identity on morphisms, because if you had a morphism that satisfied the condition for it to be a Chu morphism over here, and you apply this function, then things have to be equal, so they'll be carried to equals under the function. And in fact, that functor is always faithful, as is easy to see, but it doesn't in general. It won't in general be full unless the function is injected. So we have to ask whether we still get this representation result, or whether we get new and unwanted maps between two spaces once we cut down the set of truth values. So the first result is a negative one. If we think of the traditional possibilistic versions of quantum systems, where we just have sort of yes or no, two values, and we look at the two canonical ways of reducing the unit interval to two values, where we preserve 0 and map everything else to 1. So definitely no or maybe yes. And the other one, definitely yes and maybe no. That then in fact we get new and unwanted morphisms appearing between the two spaces. The structure is lost in some sense. The two values are not sufficient. On the other hand, if we reduce to three values, where we keep 0 and 1 sharp, and put everything else to a middle value, well, just to another value, then the representation theorem still holds. That's the only structure we need. So, yeah. Okay. So, in fact, there are interesting connections between these results and work of the Geneva School. There's a paper on the way with Bob and Isa and Frank on showing some of these connections. Looking forward, in the final bit, final few minutes, I want to look at the connections with coalgebra. So I've done things in terms of two spaces, but it's pretty close to a familiar setup for the foundations of quantum mechanics, and we can see how that works there. What I want to do now is connect it back to coalgebra. It will have to be coalgebra with some small embellishment. So let's firstly say that, I mean, apart from the fact that coalgebra has a lot of nice goodies that come with it, that whole sort of toolkit that I was describing earlier, terminal coalgebras, high simulation, coalgebraic logics, and so on, we can actually make more expressive models of the behaviors of physical systems as well. In particular, they allow us to capture the dynamics of measurement, in particular what happens after a measurement, in a way that two spaces don't. They have, as one might say, extension in time. And an interesting point is that this really picks up on something we've already seen in the examples of coalgebras we were looking at motivated from computer science. And in a sense, physics is simpler than that. Well, I mean, in a sense. But, so this is some version of the stochastic transducers that we looked at earlier. I think it's more or less the same as what I wrote down. So we have our inputs and our outputs and the probabilities here. Now, if you think of the set of inputs as the set of questions, and O is the set of answers, which we standardize by only considering yes-no questions, then in some sense we can say that quantum mechanics is less non-deterministic or probabilistic than stochastic transducers are. What I mean by that is that in quantum mechanics, if you know the preparation, you perform an observation and you see the outcome, then actually, according to the, say, the Luder's rule, projection postulate, then you know what the new state is once you've seen the outcome of the measurement. Whereas here, quite clearly, we could see the observable outcome and we still wouldn't know which new state we evolved into. So this is just a comment, but it's an interesting point, that in a sense, this standard format for non-deterministic or probabilistic computation allows for possibilities to go beyond what we currently understand in quantum mechanics. Whether there is or could be a physical theory that would contain such mild behavior, I don't know. Okay, so now let's see how we can get coalgebra as the setting for what we've been doing by starting off with an easy case. So let's take one system, fix a single Hilbert space, and fix as our set of questions the propositions, closed subspaces, or projectors on that Hilbert space. Fixing that, so we now got a fixed exponent, not a variable one as here, so we're sort of banishing the contravariance, we get an endofunctor which looks like this. So this is a sort of expanded, this is in fact closely related to the Mackey triples we were looking at earlier. Again, we've just done the trick of currying. If I brought this back over here, it will be a map from x cross q to some probability, but now I've tacked on this extra component as well. And the coalgebra for this, of course, looks something like that. And the interpretation is, as before, that x is our set of states. And for any state that we're in and any question, then the coalgebra firstly gives us the probability of getting a yes answer for the question. That's consistent with what we had here, what we had before for choose spaces. But in addition, in the case that the answer is not definitely no, it also tells us what the next state is. And here I say is rather than could be, because this simplified functor, rather than stochastic transducers, is taking advantage of the remark I just made that we are supposed to know what the new state is if we see the outcome of a measurement in a given state or a given preparation. So as a first remark, once we fix the Q, these functors are very well behaved. They're actually polynomial functors. They emit final coalgebras, which you can even visualize as sort of Q branching trees. Now, if we take an actual quantum system, a Hilbert space, this is how it gets to be a coalgebra of this kind. So this is obviously the Hilbert space that gave rise to Q as its own set of questions. So this has a well-defined meaning. So for this particular Hilbert space, this works. And here we simply got, it's all as before with our Mackey triple representation, but just with a new component where we add the new state by the projection postulate that that results if we, in the case that we get a yes answer to the question. This is exactly what the Lewis rule tells us. And I give it here in an unnormalized form in keeping with the way we've been doing things. Okay, so that's fine for one system, but if we want to have a general picture, we immediately run into a problem if we want to put it in this coalgebraic format. The first issue is contravariance, which we've already discussed. So there are really two parameters in our modelling of physical systems, the states and the questions. So if we sort of wrote this in an unbiased way, it would look like this. And as we've already discussed, although this functor is covariant in X, it's contravariant in Q. And coalgebra in its usual format does not deal gracefully with mixed variance functors. So what do we do? And of course, that was one advantage of working with choose spaces, because there we do have some contravariance. The maps on the attributes do go backwards. They go from up on the right direction. And the second point is a more subtle one. If we go back to our discussion of final or terminal coalgebras and observation equivalence, the point is you're really sort of pinning down a unique behavior for every element of every quantum system. So it's, in a sense, it's very rigid semantics under your prescribed observational scenario. So how are we going to have room inside that if sort of everything sort of has this unique. So if you think of the terminal coalgebra and you ask yourself how many endomorphisms are there of the terminal coalgebra, well, it's terminal. There's only one. There's only the identity. So there's certainly no symmetry group there that you can represent some rich group of symmetries such as we have quantum systems in there. So how are we going to accommodate that? So it turns out that essentially we can apply one construction that lets us address both these questions. And I'm going to describe it to you, and you're not going to like it, but it's going to be over soon. There isn't enough time to do it the nicer way. But anyway, this construction does solve these problems. And I should say there's an attempt at a much sort of gentler and sort of bottom-up presentation in the paper I referenced earlier, which is available on the archive. So I'm just going to hit you with the abstract story, which does give the essence of what's going on. This is how we're going to address our situation. So as we've just seen, what we have is not just a nice covariant functor, but a functor of two variables, the states and the questions, covariant in one, contravariant in the other. So it's something that looks like this. Many of the most important functors are of that shape. The question is how do you get to do coalgebra? So the way we're going to proceed is as follows. We're going to actually do a little lambda calculus in cat and curry this functor. So we get something from just a contravariant variable into this category of endo functors. So let's not worry about size. Size doesn't matter. Right, so that's the first step. If you think about it, that's pretty much what we were doing when I described that particular category where I fixed a set of questions and we just did coalgebras over that. The thing we have to add to that is that as you do have a morphism that takes you from one set of questions to another, that will actually induce a functor on the categories of coalgebras. That's where you start to get some more structure that you can use. Now, because this thing was really a bivariant functor, that's actually automatic. Because we were doing something sensible like exponentiation here, and this was contravariantly functorial, it's just guaranteed that when we curry it in this fashion, we do get a functorial map from C contravariant, but functorial from C into this functor category. So that's the first stage. The second stage is to really take up this idea of, which we mentioned briefly when introducing coalgebras, that actually you start off with an endo functor and you go from it to its category of coalgebras. Now, what one should always ask is, does that assignment extend to a functorial one? And indeed it does. And this is a well-known thing in coalgebra, although maybe people haven't made much of it. So in fact, any natural transformation between endo functors translates into a functor between their corresponding categories of coalgebras. That's the point here. So we get a functor of this shape here. And this is again a sort of, you sort of just work out the definitions. There's only one thing you can write down. Okay, so now we can compose these two things. And what we get is something that goes from a functor that goes contravariantly from C into cat. So this is what's known as a strict indexed category. Everything does stay strict, which makes things simpler for people like me who don't like too many coherence equations. So what this is doing, is there an eraser?
It's on the right.
It's on the board.
Aye.
Other side.
So what this is doing is for each object down in C, we're actually associating a category of coalgebras, which is actually going to be of, for the functor f, with the contravariant argument fixed to be a. So we actually, that was exactly the situation we were in when we fixed the set of questions. And then, because it's contravariantly functorial, this means that any map down here is going to give us a functor from this category of coalgebras to that category of coalgebras. Coalg f a prime. So that's where we've got to at this point. Okay. Now, what do we do when we have an indexed category? Well, we hit it with a Grothendieck construction, which lets us glue all these fibers together and make one big category, which sort of smoothly varies over the base and actually then has a functor vector going down to express that. So we have all these fibers, but they're not going, I mean, but the growth-of-D category is going to not only combine all the fibers, but also combine all the actions going down here in the base and the induced functorial actions between the fibers. So in this total category that we build, in this growth-of-D construction, there's lots of things happening between different fibers. And this is exactly what we need to allow enough elbow room for the representation of these symmetries. So, here's the growth-of-D construction. Well, I'm not going to, so it's a construction and it's by growth-of-D. So we take objects of the base and then a selected object of the fiber, and similarly for arrows. And then if you write down what the composition law has to be, there's only one thing it can be, and it works. So it's really combining the action down here, and then the derived action here, and then as we've transported an algebra here over there, we can then consider an arrow between an object in one fiber and an object in the other. That's really what this is doing. So the construction is, here's our functor concretely, our set of questions, our set of states. In the way we explained, we've got an indexed category from it, and then we form the growth-of-D category over it, gluing all these fibers together. Now, each of the fibers is a category of coalgebras. Each of the sort of induced mappings between questions gives us a functor between categories of coalgebras. And what we get when we glue them all together in this construction is a fiber category with variable sets of questions and morphisms which relate them relative to change in the base. And that's the kind of thing we want. So I'm simply going to summarize the sort of results that show that this works. So the first thing is, we get a nice way of looking at choose spaces. Choose spaces have been studied quite extensively, but it seems to be a new description that falls out here, because we can also see choose spaces as obtained actually from rather standard things by forming an indexed category and then applying the growth-of-D construction. So if we fix the attribute sets in choose spaces, think of Mackey triples with a fixed set of questions, but where you let the states vary, and then you only have non-trivial mappings between states. That's nothing but a slice category over this thing. So a Mackey triple is determined by a set of states and then a function from questions into values, just carry the evaluation function. And then the morphisms where you're keeping the backwards map fixed are just the sort of arrows in the slice category. So the assignment from a given set of questions to its slice category like this is itself giving you an indexed category, and again you can apply the growth-of-D construction to it, and lo and behold what you get back is the full choose spaces. So that's the first step. So we've got the same kind of description in these terms. And yeah, last slide. Okay. And in fact, we can relate the two things rather directly. As we said, coalgebras give you extension in time, and looking at the other way around, choose spaces are just a special case of these coalgebras where there is no, where the behavior doesn't evolve in any interesting fashion, what we can define as static coalgebras, and actually the choose spaces just live as a full subcategory. And this can all be done sort of quite generally for any abstract category of choose spaces. So we've subsumed choose spaces by coalgebras. And then with that relationship, it becomes straightforward to show the representation theorem for choose spaces lives in the fiber category of coalgebras. It shows that there is sufficient variation in the fiber category to overcome this rigidity of final coalgebra semantics. And in fact, it's even the case that there's a single coalgebra in which every separable Hilbert space can be given a final coalgebra semantics. So in some sense we do get to have our cake and eat it too. And this, this is saying that this fibered category allows both a suitable form of final coalgebra semantics and for the representation of the physical symmetries. Okay, so a few further I'll stop here.
I think they put the air conditioning off at 5 or so.
It's balance.
Yeah, I think it goes automatically up at 5. Any questions? Yeah.
So you were quite careful to say semantics of one system. I'm
Yes.
wondering if that means that there's no chance for a tensor product with this. So,
No, I mean that was just the sort of the starting off point. I mean just fixing one fibre. So then I sort of generalised it where you have this variation of fibres. So if you take the two spaces, of course you have a star autonomous structure there. Whether that's the modal structure that one wants is it may not be. I think actually there are other interesting possibilities for modal structures when one starts representing probabilistic structure more explicitly. But anyway, that is certainly a direction one needs to look at.
Bruce?
I'm just trying to understand that theorem about the tube spaces. So you're saying that you can accurately represent quantum mechanics by a set of states, a set of questions, and as long as the questions have only yes, no, or maybe answers, if you provide the provision for maybe, you can completely represent quantum mechanics.
Yes.
How does that, so there's the Cochran-Specker theorem or something, I remember that that's something to say along these lines. How does it relate to that?
No, the particular result here is about which arrows, which morphisms can be represented.
Yeah.
It's saying that it's only the semi-unitaries can be represented. That's the particular thrust of that result. It turns out that only these three discriminations are sufficient, which is somewhat surprising.
Yeah,
You could see it as saying that just information about either satisfying a property or being orthogonal to it, definitely, or a third possibility, which in some sense you need in order to get definite answers to the other two. I mean, if you think about a vector and a closed subspace, then, I mean, you get these three answers very naturally. I mean, either vector is in the closed subspace, it's orthogonal, or it decomposes as a sum of two things. But yes, I mean, there is, so it's kind of interesting. As I've said, I mean, it does, I think, clarify and relate to some of the things that were done by Perron and his school. But yes, I mean, it was a surprising point.
I think we all need some fresh air, actually. It's really hot.
Okay,
Let's
well,
have a